this work was done at the Collaboratory for Advanced Computing and Simulation at the USC, like next door, in collaboration with my colleagues, Rajiv, Kenichi, Priya, and then our student, Anikia, Lindsay, Hikaru, Tom, Ankit, Pankaj, Tafek, and Richu. I also collaborate with Professor Shimojo and then Professor Shimamura at the Kumamoto University in Japan. So today, I want to talk about the quantum material dynamics at the nexus of exascale computing, AI, and then quantum computing. Then let's see how it goes. So this is the motivation. So in order to develop and then also deploy a scalable simulation algorithm, we based on this DOE Supercomputing Award. So under INCITE Award, and we perform atomistic simulation on pre-exascale computers. And then we use Argonne National Lab. And then under Aurora Early Science Project Program Award, we will be one of the few initial simulation users of the 2 exaflop Intel Aurora computer to come hopefully soon. But more exciting is actually post-exascale computing, since that exascale computing is not scalable into future. And we are already witnessing so-called compute Cambrian explosion of architecture. And it is an interesting time. And then at the same time, even the quantum computer have like outperformed this classical supercomputer for some tasks. And then of course, like AI is everywhere in science and technology. So we want to use all of these advances to advance science. So today's talk is about this, the nexus of these three things. So on these platforms, we perform molecular dynamics and then machine learning. So in classical molecular dynamics, like Aidan was telling that, so we follow the trajectory of all the atoms and then study material properties. And then our focus is actually non-adiabatic quantum molecular dynamics, which treat excited electron and then whole wave function explicitly to study photoexcitation. And we also do this REACT-FF, reactive molecular dynamics, to study chemical reaction. But the most exciting recent development is, of course, the first principle-based neural network quantum molecular dynamics, which not only predict the interatomic forces, but also quantum properties like electronic polarizability. And so we do this at the exascale. So when the Department of Energy designed exaflop computer, and they published this white paper, and then where like 2 of the 4 motivating simulation images were ours. So this one is the 17,000 atom quantum molecular dynamics. In this case, to study hydrogen production from water using this lithium aluminum nanoparticle. So red are lithium atoms, and silver is the charge density around aluminum atoms. And then these green bubbles produce H2 gas. For the clarity of presentation, I'm not showing a lot of water molecules in here. Another image here, this was a billion atom reactive molecular dynamics simulation. And then what we study is so-called a cavitation bubble collapse in water near solid surface, in this case, silicon dioxide surface. And actually, we are sending the shock wave to quickly collapse this cavitation bubble. And this collapse of the bubble create a shock wave. So this is a shock wave. And these shock waves hit the silica surface to not only mechanically, but also chemically damage the surface. That's the power of reactive molecular dynamics. And so here, so this nanojet is a form, which is represented by a streamline. So the bottom line is that with billion atom, you can do fluid dynamics atom by atom. So that's the message. So to make this simulation scalable, we have developed an extension of divide and conquer algorithm, which we name Divide-Conquer-Recombine. So in the divide and conquer, the physical space is decomposed into spatially localized computational cells. And these computational cells are embedded in a global field, like an electrostatic field, which is computed efficiently in using tree algorithm. And in the divide-and-conquer-recombine, this divide-and-conquer phase constructs a globally informed local solution, and which are used in the recombine phase as a compact basis to construct the global properties. And typically, this recombine phase use we call the range-limited n-tuple computation, like triplet and quadruplet, in order to account for high-order correlation, which cannot be, in principle, captured by tree topology in a divide-and-conquer phase. Okay, specifically for order n cube, so-called a variable n-charge problem in the reactive molecular dynamics, and our order n extended Lagrangian reactive molecular dynamic algorithm eliminate the speed limiting charge iteration. We didn't do anything. We just took understood algorithm and then put it in. For exponentially complex quantum n-body problem in quantum molecular dynamics, our so-called lean divide and conquer DFT algorithm minimize its order n prefactor. So let me kind of explain this second application. So this is a divide and conquer DFT. So where three-dimensional space is a union of overlapping spatial domain. And then within each spatial domain, we solve the local quantum equation to obtain a local quantum wave function. However, here that the Hartree potential, that the potential is depending on the global density. And this global density is in turn a sum of local densities. And local density is nothing but the sum of the local quantum wave function. So we need to obtain that global potential and then local wave function in a so-called global local self-consistent field iteration. So that's a very simple approach. But the problem is that the main problem is the large prefactor of its order and cost, and which arises from this thick buffer layer we need to add in order to minimize that detrimental effect of this artificial boundary condition applied at the domain peripheries. And so in order to reduce this order n prefactor, our lean divide and conquer DFT employ adaptive boundary condition at the domain periphery, which is proportional to the difference between the local and then global density. And which kind of, so this is the convergence of energy as a function, the buffer thickness. This lean divide and conquer energy converge much faster, and then this translates to a factor of 2 to 3 speed up. And also we develop, we call the globally scalable and then locally fast electronic structure solver. And then which use real space multigrid, the tree-based algorithm to represent the global density and then global Hartree potential. And then use a plane wave basis within each domain for local electronic wave function. So this GSLF combine the scalable multigrid algorithm for inter-domain computation and then fast Fourier transform based spectral method in intra-domain calculation. So in this way, that this solver maximally expose data locality, and then thereby achieving the scalability. Okay, so on parallel computer, we divide the computation into those of domain, so domain decomposition. And then for higher parallelism, within each domain, we combine band decomposition to split the quantum wave function among processors, and then also spatial decomposition, kind of hybrid parallelization. And this is a little bit old data, but we achieve like over 98% of the perfect speed up in a weak scaling setting for a 50 million atom system on 800,000 cores. And also we get reasonable strong scaling parallel efficiency for much, much smaller, like 80,000 atoms instead of 50 million atoms. So that's quantum molecular dynamics. And neural network QMD, we are kind of tied to Argonne National Lab, so we get a similar over 98% of the perfect speed up in a weak scaling setting on the Argonne Theta machine. And then also we achieved that the GPU acceleration of the 70-fold over the CPU on a Polaris computer at the Argonne. So now let me talk about non-adiabatic quantum molecular dynamics. So to study excitation dynamics involving both electron and then atoms, we implemented non-adiabatic QMD. And then there are two requirements for this kind of simulation. First, we need to represent the electronic excited states, for which we use the linear response time-dependent density functional theory. And then we need to describe the transition between these electronic excited states, for which we use the surface hopping. And this is an example of the transfer of photo-excited electron hole at the photo antenna to this is called the zinc porphyrin reaction core in a so-called light harvesting molecule. And this is another example, the charge separation between the quasi-electron orange and then quasi-hole green in a rubrine carbon-60 solar cell. So those are typical applications. And this is an example of divide-and-conquer-recombine non-adiabatic QMD. So we studied singlet fission in amorphous diphenyl tetracyl. And absorption of a photon creates that one singlet exciton, electron hole pair. And then, but the photocurrent can be doubled by splitting the singlet exciton into two triplet exciton, spin triplet exciton. And this is called a singlet fission, but singlet fission has been limited to perfect crystal, very clean crystal. But if the high singlet fission yield is achieved instead in a disordered solid chip to mass produce, and then we will have an efficient and then low-cost solar cell. And then at USC, there was an experimental breakthrough to achieve the singlet fission in amorphous DPT. That's why we simulated this. So here, we combine the divide-and-conquer-recombine NAQMD to study phonon-assisted exciton dynamics together with the time-dependent perturbation theory calculation of singlet fission rate. And these rates are recombined in the kinetic Monte Carlo simulation of exciton population dynamics in the 6400 atom amorphous DPT. So this is showing that, again, orange and then green electron and hole. So what we are seeing here is, so the first part is basically like a diffusion of this spin singlet exciton from molecule to molecule. And then at the end, you see a fission into two triplets. Eventually, we observe the fission. So that's the NAQMD divide and conquer. And then this is the computed population of spin singlet and spin triplet excitons as a function of time, no fitting parameter. And then which agree very well with the pump probe experiment at USC. And then especially, we reproduce this 2-time scale around 1 picosecond and 100 picosecond. The same as experiment, we are able to explain it as a consequence of like a singlet fission hotspot in the exciton hopping network. So here I want to emphasize the synergy between our INCITEIAURORA project and then our MAGIC Center and then LCLS experiment. So we have a DOE Computational Material Science Center called MAGIC material genome innovation for computational software. And then MAGICS is affiliated with the world's first free electron X-ray laser at LCLS, and also ultra-fast electron diffraction facility at the SLAC at Stanford. And these facilities perform pump probe experiment to study photoexcitation dynamics in femtosecond time resolution. So, and then our INCITE and the Aurora ESP simulation reproduce the study this photoexcitation dynamics at exactly the same time and then spatial scales as experiment. So this is one of the example. It's a extremely strong laser, and then we found that the strong laser light is almost like a 99% quantum efficiency transformed to that lattice motion. And so in molybdenum diselenide at the monolayer. So NAQMD simulation reproduced first rapid photo-induced lattice dynamics. So this is that so-called Divide-Waller factor, kind of disorder of that lattice. And then one is the perfect, and then the deviation from one is the disorder. Within the picosecond, that the photon energy is converted to lattice energy. You computed the quantum efficiency is very high. And then also we reproduced that so-called mono-exponential, 1 time scale to bi-exponential, 2 time scale the dynamics at elevated electron hole density. This is the low density blue and then high density red. And so actually, so this is the simulation. Experiment is here, kind of very similar. And then so the simulation, we can explain why it happened. So that this lattice, rapid lattice dynamics in the picosecond was explained as a softening of the endpoint phonon. So this shows that the phonon dispersion at the elevated electron hole density. So we see that the softening of endpoint phonon at a certain electron hole density, and that is reflected this rapid disorder. And then this is the endpoint phonon. And then at the higher electron hole density, another, the mode is softened that provide an extra decay channel. So you see like a different time scale. And then after that, we also simulated photoexcitation dynamics in tungsten diselenide monolayer on alumina substrate. And this shows that the root mean square displacement of both in-plane and then out-plane atomic motions as a function of time. So upon the photoexcitation at the time 0, we see that enhanced in-plane atomic motion. And this shows that the distance between like a top and then bottom tungsten selenium layer. And we see upon the photoexcitation, the photo-induced that the contraction of tungsten selenide distances. And this can be again explained by that the change from like a bonding to anti-bonding character through that photoexcitation. And this is a good agreement with the femtosecond surface X-ray scattering experiment at LCLS. So more recently, to study light matter interaction in more detail, we have developed a DC mesh method. This is called divide and conquer Maxwell plus Ehrenfest plus surface hopping approach. And the DC mesh consists of 2 parts. The first part called LFD or local field dynamics, and which solve the Maxwell equation for the light, and then real-time time-dependent nesting function theory equations for electron to describe light matter interaction. And the second part is called the QXMD, quantum molecular dynamics with excitation, describe non-adiabatic coupling between electron and then ionic motions based on the surface hopping approach. And this LFD and then QXMD handshaking is achieved by using electronic occupation number. So that's the information shared by two programs. And then here we also develop so-called globally sparse and then locally dense solver, which is again the key to scalability on the modern exaflop architecture. So where inter-domain Hartree coupling is achieved again by a scalable sparse multigrid method, whereas that intra-domain actually heaviest computation turned out to be non-local exchange correlation computation, and that was mapped to basic linear algebra +3 matrix computation, so that to use a GPU. And I will skip the details. So this local field dynamics at the Hamiltonian consists of electronic Hamiltonian and then electron ion Hamiltonian. And then we use the Trotter expansion to exponentiate each Hamiltonian in LFD part and then QXMD part, and then using some numerical techniques. And so here, what we did is the QXMD is actually wave function is resident on the CPU to do more chemically accurate computation. Whereas this the LFD wave functions are resident on GPU, and then to do kind of simplified that quantum dynamics simulation. And I'm kind of borrowing that Anders' word that the shadow dynamics is performed on the GPU, and then so they only exchange minimal information, like occupation number change through that the light matter interaction is passed to GPU to CPU, and then after moving atoms, local potential change that is passed to CPU to GPU. But the wave function we are not sending back and then forth. Okay, so we also have a multiscaling method in which excited state non-neural network quantum molecular dynamics learned excited energy landscape produced by this first principle DC mesh, so that we can do much bigger system. More recently, we have also developed a multiscale NNQMD method. So here that the multiscale quantum challenges, we are studying kind of ferroelectric topological material. And that complex response of this ferroelectric topological defect to external stimuli like light and then electric field or mechanical stimuli encompass the picosecond to nanosecond time scale and then nanometer to micrometer length scale. So we cannot do first principle. So we solved this challenge taking Q from the multiscale QM, MM, or quantum mechanical molecular mechanics method, for which my colleague Aria Varshel got the Nobel Prize in 2013. So in our group, we are also combining the multiscale QM, MM, and then finite element FE method. So this is showing is that the enormous dissociation energy of oxygen molecule on silicon surface is propagated from the small QM region to like bigger MM region to finally to the finite element region without noticeable like a reflection at the artificial model boundary. And so we have been doing this. So like more recently, like last year, we just extended this to NNQMD. So here that the neural network quantum molecular dynamics for ferroelectrics, like a PTO, is embedded in the cheaper molecular mechanics for ferroelectric to apply appropriate strain boundary conditions. So that's the kind of cover of recent JPCL. So the exciting application of that approach is we call the ferroelectric Opto-Topotronics. So quantized ferroelectric topology, such as a skew muon, is protected against thermal noise because of this integer topological number. So this may enable future ultra-low-power optoelectronic application to fight against thermal noise. And then our billion atom excited state neural network QMD simulation revealed photo-induced topological phase transition and dynamics. This is similar to so-called Kibble-Drake mechanism. So photoexcitation, this ferroelectric order is destroyed. So there's kind of like a, it will create a kind of like a defect. And then this is called a cosmic string. And then also it, at the same time, create another kind of like a tilting order parameter. So this is the photoexcited change of the like order parameter. We also observed the symmetry-controlled skyrmion to skyrmionium. Sorry, I cannot pronounce it. Switching. So here, skyrmionium is that the composite, topological composite of skyrmion with opposite topological charges. So, but we found that under symmetry breaking strain, and then we can annihilate this skyrmion topological defect topology. On the other hand, if you do symmetry preserving compression, then the annihilation, then you can convert one skyrmion to like a skyrmionium. So again, that topological change can be controlled by symmetry. So, so about this neural network. So kind of like a general neural network, but in our approach, neural network not only predict atomic forces, but also we predict other things like a maximally localized Wannier function centers to compute a quantum property like electronic dipoles. So several neural networks. So recently, Aidan kind of introduced, but we employ a neural network model called Allegro, or called FAST. And this is that very recent paper from that Boris Kozinski's group at Harvard. So they achieved the state-of-the-art accuracy and then also speed. And this speed, that's why that Allegro means fast. This is founded on that group theoretical equivariance and then also local descriptor. They used to do the graph neural network. That was too expensive. But by changing to local descriptor, the same accuracy but becomes so fast. However, it doesn't work sometimes. So on massively parallel computer, I think that Aidan's like a last comment, robustness haunt us. Growing number of unphysical force prediction, we call adversarial forces, prohibit simulation involving large number of atoms for longer time. It just destroys the simulation. So this is the number of force outliers, the number of like unreasonably large forces as a function of molecular dynamics step. Allegro still break down after millions of time step. That's why we developed a new method to suppress that the breakdown. So, so we call this a fidelity scaling problem. So we solve this fidelity scaling problem by developing a so-called Allegro-Legato. So Allegro is fast, and legato means the smooth. If you're a musician, you understand. So we use the so-called sharpness-aware minimization. Add the loss function, we add the kind of like the regularization to make that the Hessian of that loss with respect to this neural network parameter to be small. So it's smooth. Okay, so it enhances the robustness through improved smoothness. So, so we are able to just accept the paper, able to elongate the time to failure scaling. So time to failure is the scale with the number of atoms. That's why it's very difficult to apply neural network to large system. But we elongate this without sacrificing accuracy or speed, exactly the same speed, exactly the same accuracy, almost. Achieving we call the spectroscopically stable long-time Hamiltonian trajectory. Of course, you can put the heat burst to suppress that big force, but you want to do spectroscopy. You need to have a Hamiltonian dynamics conserved, and that is very hard. So this is the time to failure as a function of the number of atoms, and then Allegro, original Allegro, like that the time to failure become quicker and then quicker for larger system. But the Allegro-Legato can kind of keep that long time to failure.
Aiichiro, the Hessian evaluation, a naive implementation of that is order n squared. So
yeah, very good position. So this is that proxy. So it kind of like we set some kind of perturbation radius we define, and then kind of put the randomly display. So the cost is linear. Yeah, you are right. If you do literally Hessian, it's kind of curious. So that's one of the innovation actually. Yeah, thank you. Yeah, that's the important point. So this is the example of so-called this we call the spectroscopically stable long-time Hamiltonian dynamic. And so we implemented nuclear quantum effect into neural network quantum molecular dynamics using a passive integral molecular dynamics like this. So each atom is this ring of kind of this beads. And then, so that represents kind of like a nuclear quantum effect, especially for hydrogen. So neural network QMD trained by Aiichiro QMD achieved the required large number. So lower temperature, you need to have a larger number of beads. And then of replicas at low temperature, and then long-time Hamiltonian dynamics to resolve fine vibrational structure by Fourier transform. So this is that Aiichiro QMD, and then, this is the ammonia. And then we had collaborated with the Oak Ridge National Lab, the first high-resolution vibrational density of states of ammonia. And then we did QMD, and they didn't agree at all. And then we needed to put the nuclear quantum effect with this Allegro passive integral, and then that's right on top of each other. So that's a kind of like we couldn't do that without this Allegro-Legato. Another thing we implemented is to incorporate the charge transfer for accurately describe chemical reactions through charge equilibration in reactive molecular dynamics. So basically, the electronegativity given the electronegativity, like a charge is obtained at every MD step. So this shows that the charge transfer from aluminum to oxygen during the oxidation of aluminum nanoparticles. So we kind of incorporated this charge equilibration part to neural network. And this was kind of named by other group, that the fourth generation NNQMD. And then basically we apply Allegro-Legato to achieve the same smoothness and then robust long-time dynamics within this 4G neural network. Okay, so now let me talk about some software. And then we have a software suite called that AIQ-XMaS. That's the AI and then quantum computing enabled extra quantum material simulator. So the part I explained is the QXMD code for non-adiabatic QMD. RXMD NN is kind of like a simpler version of LAMPS, which can do both reactive and the neural network force field. In addition, we have Mystics, that's a quantum many-body dynamics on quantum computer. We also have something called a MaiTai AI tool for material design. So let me kind of describe this part now. So example of MaiTai is a reinforcement learning. So just like that the AI play a game of Go, we use the reinforcement learning to design optimal growth condition to achieve desired property. So for example, so this is the chemical vapor deposition of molybdenum disulfide. And then using the sulfur gas, H2 gas, H2S gas. So the control knob is the temperature and then the partial gas pressure. So that's the action by a reinforcement learning agent. And then, so this action is converted to the state change, but not using reactive molecular dynamics is already expensive. So we train a proxy, kind of neural network-based dynamic model to predict this, and then in order to achieve the better quality product. So this is an example of computational synthesis of molybdenum disulfide. So here, we found a very interesting transformation pathway to the stable 2H phase. 2H phase is the global minima. But it turned out kinetically like a non-equilibrium. It first goes to metastable 1T phase during the CBD growth of MoS2, and then finally become a stable 2H. So here, blue color is the disorder, and then 1T is the metastable 1T phase. Then 2H is the eventual stable final product. Oh, sorry. So let me play a movie. So you see from random, first you see green, that's the metastable phase. That first kinetically more accessible. So it go there, but eventually it find that like a global minima. And then 2H phase, and then the grains surrounded by the grain boundary. So that's the kind of realistic structure we can grow with the molecular dynamics. And then more recent computational synthesis actually focus on the so-called active control of transition metal dichalcogenide oxidation. So TMDC, everybody said is the kind of next generation that the ultra-low-power electronics should come from, this TMDC, that's a semiconductor. But to have a device, you need to have an insulator and then semiconductor. And then the proposal was the oxidation of TMDC was proposed as a scalable synthetic pathway to semiconductor insulator interface. Like my friend at Raf Haramiro at MIT is really pushing this direction. And then, moreover, the Raf and then some other people, not just a passive oxidation, but the active oxidation as a quality control. So active means oxidation enhanced by the plasma, UV, or laser, or pressure, like in a pressure chamber. So we did a reactive molecular dynamics simulation to show that the pressure control of active oxidation. And then we found that this 2D oxidation proceed in a stepwise, layer by layer, slow oxidation, and then this the reaction control, linear oxidation, and then diffusion control, parabolic oxidation. And then that three stages can be controlled by different pressure. So that's the actively controlling for future 2D electronics. But this is still nanosecond. The real growth is second or longer. So here again, the reinforcement learning comes. So we use the reinforcement learning agent to autonomously discover low activation barrier migration pathway to study long-time dynamics. So here, multiple agents share so-called replay buffer kind of experiments. They share experiment to become smarter and smarter. So and then once that this agent find that the migration path, we estimate the migration time using the transition state theory. So this is one of the migration paths of water in silica. And this is the energy profile along the path from which we can compute the time. And this is the 2-second trajectory. We cannot do that molecular dynamics. So you can see let me see. So agent is kind of it's a very non-trivial path. So this is just started, 20 seconds, 30 picosecond, 1 nanosecond, 14 nanosecond, microsecond. I think there's a very high barrier it crossed. Yeah, here. It was impossible to find this. So right now we try to kind of serialize this. So we can do some non-equilibrium statistical mechanics. Right now we're just finding a path. So, but we see a lot of potential. So finally, quantum computing. So how to use it for science? So first of all, what is quantum computing? Quantum computing utilizes quantum properties such as superposition and then entanglement for computation. So this is for interaction. Superposition is a quantum parallelism. And then US Congress signed the National Quantum Initiative Act to ensure the US leadership in quantum computing and its application for security and then other applications. And then followed by the quantum supremacy. That means quantum computer is faster than the fastest supercomputer, demonstrated by Google, this 54-qubit C common computer. And then for us as a scientist, what is the most exciting quantum computing application? Which is as a universal simulator of quantum many-body system, which was promoted by Richard Feynman. And despite some success in simulating static properties of quantum system, like ground state energy of small molecules, it remains a very hard challenge to simulate quantum many-body dynamics on current to near future, so-called noisy intermediate scale quantum computers. Number of bits are not so big, and also it's extremely noisy. The fidelity is so low. So we successfully simulated non-trivial quantum many-mode dynamics on IBM-Q and then Rigetti-Aspen quantum processors. So we simulated the electromagnetic field or terahertz control of quantum state in a chain of rhenium magnet in molybdenum diselenide monolayer, just like here. So here, Hamiltonian is kind of like this transverse field Ising model, and then this transverse field comes from through the spin-orbit coupling, a kind of terahertz phonons. And then the spins are mapped to qubit, and then we just construct a quantum circuit to do this time propagation. It's a very simple circuit. And then as a user, you just write a Python program and then just give it to cloud access. So that's the system. This is a molybdenum selenium, and then the rhenium introduced one extra electron, which has a spin, and then have a magnetism we published some years ago. So this shows that the result, that the average magnetization as a function of time, this is an increasing terahertz radiation fluence. You can see that effect. And this red is the quantum computer, noisy, but kind of this simulator is kind of ground truth, kind of following this, despite this noise. And then done by this Lindsay Busman. And then since the noise is a big problem, so to mitigate this environmental noise, Lindsay also developed AI-based quantum compiler. Quantum compiler is kind of like a heuristic search to achieve the same functionality with a less number of gates. Therefore, compound effect of that noise is reduced. And then we also have a full stack cross-platform software to do this quantum dynamic simulation on a quantum computer called MISTI. So Lindsay graduated in 2020 and then was at Lawrence Berkeley National Lab. And then late last year, she moved to Italy as a Maria Curie Fellowship. And then this year, she also got something called a Science Research Award from Italian government. So doing very well. So now let me just mention the application of those software for our future manufacturing project in between Princeton and the USC and the Howard. So here we develop AI and then robotics guided scalable manufacturing platform, like a robotics platform using nanofluidics in order to the manufacturer precisely align this the van der Waals heterostructure like Lin was talking about to enable future electronics. Finally, education is very important for us. We train a new generation of computational scientists at the nexus of not only exascale computing, but the quantum computing and AI to support that kind of new generation of, we call the cyber computational scientists. We have a unique dual degree program in which students get a PhD in material science or physics or chemistry or all these physical sciences, along with MS in computer science, specializing in high-performance computing and simulation, has been here for 20 years. And the new one is the MS in quantum information science. We just got the second batch of students. It's brand new. Also, we have a MS in material engineering with AI. That's also brand new. So those are at the dual degree to support this nexus. And we have NSF Cybertraining project called CyberMagics between USC and the Howard University is the historically the minority school in Washington, D.C. Okay, so let me finish with kind of application I didn't talk about from our group from the recent cover. So we study a lot of this green ammonia for renewable power generation. We also developed some molecular design, kind of new descriptor enhancing smiles, like smiles. And then this is the phase change memory, kind of like a GET, and then so on. And then the most recent one, this just published one, is that so-called strain self-assembly. So what we are doing is putting a 2D material on the shape memory polymer. And then if you compress, it creates something called a Miura-Ori pattern. And then that is very deterministic. And what happened is, it is known that you have this curvature in the 2D material, it can work as a quantum emitter for quantum information science. But the problem is very difficult to deterministically put a quantum emitter or the diamond like this vacancy center stochastic. So this, we think, may be the way to put deterministically put a quantum emitter for quantum information science. Okay, with that, let me stop. So, so large spatial temporal scale quantum reactive and neural network molecular dynamic simulation can be achieved in a common algorithmic framework we call divide-conquer-recombine. And then this AI plus quantum for science has a lot of application into future. So with that, so this is our the funding source, and thank you very much for your attention.